So this is an anomaly. Okay, it's something that's not expected. Anomaly is something anomalous, gets us by surprise. Bilady's anomaly only occurs when you have certain replacement policies, but it is a kind of a counterintuitive. There's probably a good video on it. Let's see. You guys can click on it right on your own. Okay, we'll get into here, but okay. Any other discussions that we can try some more traces?
Those 4 words in like a little section, what would that be called?
Yeah, it's a good question. What is this one? Say again.
How there's 4 words total. Yeah. Right.
This is great. So you want to start getting these things. This is the contents of cache. So this is a depiction of this is the representation of cache memory inside the CPU. The CPU is not the world's biggest CPU. It's probably the world's smallest CPU. It has 4 word capacity in cache. Let's look at, you know what, now's a good time to actually define these here. So let's do this. So we're told here that each cache line holds 2 words. So this is a line. That's a line. 2 words. Each line has its own tag. This whole thing is the contents of cache. In this cache, how many word capacity is this cache? 4. If I told you that the word size was 4 bytes, like MIPS, how many byte cache is this? You go to Dell and you're going to buy this chip, and you're going to be very disappointed. It's not going to work too good. But what did it say in the specs for this chip as cache capacity? How many bytes? 16. Yeah. Because you have 4 words. Each word is 4 bytes. It's a 16-byte cache. So when they see, this is back to what I call the Bright House Networks problem, right? You know, so many 50 megabits download, right? It's a bits. Bits is not bytes, right? So you download your file, and it's pretty fast these days. We don't even notice it, right? But back in the old days, it was a different world. Anybody ever use a dial-up modem?
14.4.
14.4, okay.
Only kind of late.
All right. So I started with 300 baud, so that's 300 bits per second. So 14.4 is 14,400. So that's a factor of what? 20, so 30 minutes.
300 baud, right?
300 baud. 300 baud.
Yeah, was typing.
You would see it go like this.
Yeah.
It's a little bit faster, and it's consistent, right? Because you make typos, right? But this go like about that. So acoustic couple, right? Actually, phone line. We don't even use phones anymore, right? Like that. We cell phones, right? But this is a totally different world, actually. If you wanted to do computing from home, if you had a home computer, you were a very rare situation, but you'd have to call to where the data was. We didn't have internet, so you'd call. You pick up the phone, you dial a number, and people would, they would manage these bulletin boards and these access, so that they put modems in next to their server, and you can call in. They'd actually rent a number from the phone. They buy, a number from the phone company. You dial that number. You hope it's not busy, because it's only one channel at a time it can transmit. If it's not busy, your computer talks to that one. It's usually acoustic couple. We had these handset things, right? You'd actually plug it into this little, have like styrofoam, or I don't know.
It's like in the movie War Games.
Yeah, but it was real life actually. But yeah, so you plug it in and you hear ee. It's actually converting all the bits to sounds, so they can be transmitted. How do we get on that? So yeah, transmitting back. So this is a 16 byte to cache. Yeah, not very big. Other questions on? Yeah, see, back in the old days, we would have to the fastest way to get it done. When I took my freshman year class, we had same as 3211. We had everything on campus was 300 baud. Except the computer room, because the server was right there, the mainframe. They've changed names, right? It's like not cool anymore to say mainframe. But it's the same as the server. The server was there. You would go to the server because it was 9600 baud. But they only had 5 of those terminals. So like to get your job, can you imagine debugging your program if you could only like see that it was the worst thing? You have to write 5 pages of code and get it to work, and it prints this fast. So what would you do? You go to the computer center where it's faster connection. It still wasn't that fast, 9600 baud. It would be like a line at a time, maybe 1 line per second. You'd go there and do that. All right, so back to cache. What about this? We see this is a contents of cache. It has both data and tag. A tag is some portion of the address. Some bits of the, not the complete address. We don't need the complete address because some of the bits have certain meanings that's deterministic. It's already decoded for us. The only part that we have to check, just like the code check, if I'm using the lower bit to tell me the bin number, I don't have to check that. I just check the upper bits of the tag. Other questions? That's a good question. Other questions? This one. So we're going to say, how do you calculate this? If someone says it's a 16-byte cache, how do I know it has 2 lines and 2 words per line and so forth? That's what this calculation was. So now it's time to do that. Let's start with direct map cache, and usually they'll tell you the capacity of the memory in bytes. You have 4 gigabytes of memory. So it's usually some power of 2, and A is the power. So if memory is byte addressable, and this course is always byte addressable, and almost in the whole world it's byte addressable, then the width of the address bus is A bits if you have 2 to the A byte capacity. I've been leading you along that path since we started. I kept saying, if you have 32 bits in MIPS, what's the addressable space? 2 to the 32 is 4 gig. I'm making 4 gig. 30 is gig. 2 to the 2 is 4. So 32 bits gives you 4 gig. So if A is 32, you get 4 gig addressable space. That's the maximum memory size. How big is your cache? We have 2 to the n blocks or lines, because blocks and lines are the same. And you're going to say, where do these letters come from? This is actually from the author. So he uses A for this exponent, which is kind of okay because it's kind of like address. And N, he just used N, so we just roll with it as N. And then block size is 2 to the M. Okay. And we're going to see an example in a minute. But if it's a 32-bit machine, each byte, there's 2 bytes per word, so you have 2 bits to tell you the byte number within each word. So you actually have M plus 2 bits. We're going to see all these come together in a second. So then you can compute the size of the tag field. The tag is basically whatever's left over. In other words, you start with A bits, because every memory address has 8 bits. That's processor to memory. That's the channel, is the address bus. And we're used to tell you which line of cache it is. M is actually telling you what word it is within that palette. So this is the number, this is the log of the number of palettes. This is the position within the palette. 2 to the position, right? And this is the byte within the word, which is basically like inside the box of cereal, I guess. I don't know. So it's like one of those packages, right? You buy these, they call it healthy snacks or something, right? Snack size or something. You buy the box, right? But then there are 100 calorie packets inside. So that's the number of bytes per word. So the word is like a box, but inside you have 4. Right? So the question is, how many bits total are there in the cache? And this equation is given for you in the book, but I'll show you an easier way to calculate it. But basically, the number of bits per line times the number of cache lines. They're going to give you the number of cache lines, or they're going to give you memory capacity, so we can get these exponents, which we're going to do on the next slide. We solve for n. So somebody tells you 4 gig, you have to say 2 to the A equals 4 gig. If somebody tells you have 16,384 lines, you've got to solve 2 to the n and solve for n. What power of 2 is 16,384? It sounds like a hard problem, but 16,384 is 16,000. So what's the nearest power of 2 that you know is 2 to the 10? So that's 16k. So you need 10 bits for a k, and how many bits you need for 16? 4? So it must be n was 14. Can you do those kind of things in your head? Yeah, if you're already power 2, which memory is always a power 2, you can use what I showed you. It's really helpful, and you'll be in project meetings talking about address buses and data buses, capacities. Break them into units of 10 bits at a time. So then this one is the number of bits required per line. What's in a line? We have what? The bits of data and the bits of tag and 1 bit of valid. 1 bit of valid, sorry he wrote it backwards, but there's 1 bit of valid. We saw it, right? Well, it's right here actually. 1 bit of valid. These are not stored anywhere. These are the address outside the mailbox. This is the contents of the mailbox. What's in the mailbox? Some bits of tag and some bits of data. How many? Well, 1 bit of valid. How many bits of tag? We said tag was whatever's left over. Minus 2, because it's, like I said, we don't store that word within the line. Word within the, sorry, byte within the word. Then, how many bits are there of data? Well, each word has 32 bits, and we say 2 to the m is the block size, so it's 2 to the m times 32. Is this equation. I'm going to show you an easier way to calculate it soon, but here's an example. So here's a problem. It might be on the final exam in some form. You're given 16 megabytes of byte addressable main memory. Cache capacity is 64 K bytes. So now you go to the Dell website and the L1 cache is 64K. Actually, that's not too bad. It might be 32K. 64K, okay. Block size is 4 words. That's a little small, but it's okay to this problem. But in practice, you're going to say, well, how big is the block? How big is the palette? Usually about 128, maybe 128 words is transferred between main memory and cache when there's a miss. It could be 256. It's up to the designer. It could be 64 or 32. It's usually not more than 512 or 1,000. Yeah, it'd be very rare. So the first question is, how wide is the main memory address bus? So we have to solve the equation. 2 to the a is 16, is 24. How did I get that so fast? What's the nearest power? Yep, 20 plus, yeah, yep, you got it. How many blocks are there in main memory? Well, main memory is organized in blocks. Main memory has this many bytes, but how many bytes are there per block? Well, there's 4 words per block, and each word has 4 bytes, so you have 16 bytes per block. So you have 16 megabytes, 16 bytes, you must have, this is 1 meg in decimal. How many lines in the cache? 64K is the bytes capacity cache. You got to watch the units. It's not lines, it's bytes in this one. Just like a Bright House problem, right? Bits per second, not bytes per second. So this is the number of words in the cache. We just solved for that one. We can handle that because we have 4 bytes per word. So this must be the number of words in the cache. The block size is 4 words, so we're going to divide that by 4. Now when we divide by 4, do you have to put this number in your calculator and expand it out to this big decimal? You want to divide by 4, how do you do it quick?
2 to the second.
You got it. So subtract 2 from 14, 2 to the 12. What's 2 to the 12? Well, you know 2 to the 10 is 1K, so 2 to the 12 must be
4K.
You guys are pro, like that. So what is this problem telling you? Well, you get points for doing this, but it's nice to know what you just did too, right, sometimes. So what did you just do? What we did is we had in memory literally 1 million blocks that could map onto only 4,096 lines inside the chip. That attendant's job is, he has a tough job, right? That's the memory controller in this particular chip, but it's pretty typical, right? And we said main memory increases by each level a factor of 1,000 in capacity, more or less. It's a rule of thumb. So, you know, we have a 4,000 here, you're going to have 4 million out in main memory or so. And there's a question. No. Oh, yeah. Good.
I noticed we're not accounting for the valid bit, then we put the capacity.
Yeah. So what's interesting is that this is actually always a point of ambiguity, and sometimes you have to look at the data sheets to see what you're actually getting for your money. The general convention, like it's, I don't know what the word is, but I was going to say gentleman's agreement or whatever, but if you just say how many bytes capacity, it's normally for data. They don't gyp you on, reserving some of those for overhead. Okay, but it can go both ways, right? So, like if you buy a hard drive, they'll say formatted capacity. So many, 3 terabyte or 2 terabyte hard drive, and they'll say formatted capacity. Some 1.7 or 1.8 gig, terabytes. Why? Because there's overhead for the operating system. They have to break it into sectors, and they have to store blockchain, everything they put on the disk. So that's operating systems class. But the same thing here. Normally, if they tell you the cache capacity, it's of the data without the tags and without the valid. If you don't like to memorize equations, which I don't, is there another way you can calculate the number of total bits in the cache? Let's jump ahead and see that. Actually, I think this may be the next slide. Let's jump ahead and do it. This is the same problem that we just did. This is using the equation that we just had. You maybe remember that equation, but without any equations. So this is relating Jack's question, what are we looking at here, to actually what we're actually counting as contents of cache. So here's an example. You're calculating the cache device area. So this is very important. Okay, so now you're on a design team and they give you some area budget. You want your chip to be faster because then your stock price goes up and you get more stock options. So you have to make this cache as large as possible. So you have basically determine the area on the chip for the cache. Now that's going to include the tags and the valids. So we have to figure out, we have this area budget, which is the red box. How big of a cache can I fit in here? Well, I have to have one valid bit for each line. I have to have tags, which is whatever's left over from the address. And then I have to have the storage for each word. So let's give us some numbers and just try. Example. You have 8-line cache, and there's 2 words per line. So we see 8 lines of cache. They'd actually be numbered 0 through 7 in this binary. And that's going to have a total capacity of 16 words. The word might be MIPS. If it was MIPS, then we'd have actually 64 byte cache. Okay. What's the line size? The line size and block size are the same. So if they tell you that there's 2 words per line, that means the block size is also 2 words. Questions now, what's the tag? Well, we have to figure out, first of all, in this case we have only 2 words per line, so that's just 1 bit. What's the main memory capacity? That's a good question. Well, I had to tell you the capacity here in bits, the previous slide. So main memory capacity from here, I can have to look at these bits. Memory capacity in this case was 8 bits. So there's 256 bytes in memory because memory is byte addressable. So you can see what I drew it over here, and now we see it in detail. This is address 0, byte address 0, byte address 4, byte address 8. So it's actually the 0th word, then the next word, the next word. But we see that the lower bits are always 0. That's why we don't store them. Lower 2 bits. Because we have 2 bytes per word. If I go up by word, they're always going to be zeros. Then the next bit is telling me the word either left or right. See, when this bit toggles, you go here, 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 here. As this goes 0 or 1. This is telling you when it's a 0, you're in the left. We call bank, okay? We use the word bank. If you see memory banks, that's the same as bins when you're the code attendant. So when this bit is a 0, you're in the left bank. And when this bit is a 1, you're in the right bank. What line are you in? Well, that's the next set of bits. How many bits? Well, if I have 8 lines, I need 3 bits. We're going to say in this machine there was 256 total, and you used up 1/4 of that. So I still have 2 bits left over. What do I do with those? Those become the tag. These are all tagged with the same data. Good question. If they're all tagged with the same data, can they simultaneously reside in cache? No. Because I can only store this or this or this or this, because they're all going to be mapped if they're mapped to the same line, right? So let's take a look at the size of this as our last thing for today, and then you can do an extra credit if you like. It's Wednesday, right? Yeah. You know you're working too much if you check what day of the week, right? So you can use this formula and come up with 536 bits are inside this box, but there's an easier way, right? So what is how many bits are in this rightmost box here? 32, okay, and another 32. Then tag we said was 2. Tag covers the whole line, and plus 1 for the valid. How many lines? 8. Oh my gosh, that's a lot easier than remembering all this. So that's the way I do it. It turns out this is the same number, 536. So when we come back next time, we're going to try some more address traces, and we're going to actually have new ways so we get rid of this conflict problem, making it going beyond direct map. We're going to make it associative map to handle some of these other types of misses. We're going to do just a couple more examples. It's good to look ahead of time, maybe, if you want to see these. We're going to use associativity to get rid of this conflict. We're actually going to make the cache mapping flexible, be able to associate with where this word comes from. Associate any word in memory with any line of cache. We're going to break that rule. But then we have more work to do. So this is Monday, and we have to start, slow start, right, and ramp up here. Here we have what I was speaking about. Of course, in the old days, you see they used a movie projector. What's a movie projector? What's a movie projector, anyone?
Movie projector?
What's a movie? before right? MP4, yeah. So you get film, right? And it had little still pictures, and if you move the frames fast enough, it looks like it's a movie, right? But in the old days, you have to have bright light like we have in the projector, and then you shine that through the film and it projects the image. So anyway, the physics professor had this rotating arm on a motor, and it was, I don't know, a tennis ball or something on the end, and it was going in a circle like this. But if you look from one dimension, it looks like the same as a sine wave motion that we see here, but actually it means in another dimension there's something rotating in the circle. And this video is going to start this way, and as this video proceeds, it's going to rotate it in the plane, and you're going to see the change now when he rotates in the plane that now we see now motion. So this is the 2015 equivalent of so as somebody came to my office hours, said, "This is going to be your retirement?" I said, "No, this is inspiring me for my retirement to take some more quantum mechanics and think more about the universe," right? Because what I'm thinking is, anytime we see this type of sine wave behavior, it means something's spinning in another dimension. Yeah. Anyway, that's for retirement, right? Okay. So what we're going to do today, we're going to continue in cache. People that are vlogging, I've had a few vlogs come in. We like to see those today, so I can look those over and come up with some questions. Write up some questions for the spectators. We'll have a vlog, I guess it's not this Wednesday, but a week from Wednesday. And send me that. So we did the field definition last time, and we looked at the ultralight, I believe, in this class, and we kind of ended on this hardware view. So this is a good place to start. So here's a question saying, from the previous slide we had values of 256 bytes main memory. How many bits on the address bus? So we had 256 bytes of main memory. How many bits wide is the address bus? So we're solving the equation. 2 to the a equals what? Nobody? 2a equals, memory is always byte addressable, 256. Oh my gosh, guys. Okay, I know it's Monday, but we have a 1 video limit. We already tried waking you up. What's A?
8.
You got it. Okay. So Neil's with us here. So A is 8. Where do we put that on the diagram? Is it red or blue?
Red.
You got it. Okay. So we know this is 8 bits here. And then there's a 64 byte direct map cache. What do we do with that? We're going to solve for what? N is the cache, number of cache lines, right? But if the units here are lines. What's a cache line? Is it bytes?
Well,
It's in terms of words per line, so we need to know the word size. This is MIPS. So how many bytes per word in MIPS? Bytes per word. I know 32 is, I shouldn't tell you guys that. 32 is the most, if you don't know, guess 32. It's still right to the best guess you got, but if it's bytes per word in MIPS, is how many? You got it, okay. 4 bytes per word, okay. So we had also, right, solving the number of bytes per word. So here, if it's a 32-bit, well, don't worry about 32-bit, but it's 4 bytes per word in MIPS. So we're solving 2 to the W equals, so 2 to the W is the number of bytes per word, was 4, implied W is 2. Actually, we already solved these on the previous slide. Right? But then, what about lines? Cache lines, we have to figure out how many words are in the cache. Well, there's 64 bytes in the cache. How many words would that be on a MIPS machine? You're going to take it and divide by 4. Ah. So there's 64 bytes in the cache times 1 word per 4 bytes. You with me? Is 16 words. We're good, right? So we have to solve what? 2 to the n equals 16, implies n equals 4. Or was I thinking 3 here? There's 8 lines. There's 2 words. I didn't read that. There's 2 words. Yes, I didn't get to this part of the sentence. It's important to read the question before you. So there's 2 words per block. Block and line is always the same. So I have to divide. So this is actually 16 words in the cache, but there's 2 words per line or block. So there's actually 8 total lines, 8 lines in this cache, which implies we have to solve 2 to the n equals 8, means n is 3. Okay. You need to practice. It's not, everything's here, but you have to try some examples, okay? They're going to have different word size, different number of bits, different address bus, but the point is, we want to use that to design the hardware. If we looked inside the chip, which I see some vlogs coming in, and people did this, and they're actually going to talk about cache sizes, pretty cool, for some mobile devices, A9 and some Snapdragon and Android and so forth. This is what's actually inside. So in this case, there's 8 on the address. So what about the number of lines here we just solved for? That was 8. We're good with that. If there's 8 wires on the address bus here, 8 signal lines, how many are coming out of the cache? If you miss on main memory, if you miss on cache, you go to main memory. How many? If that 8 here, then the same. Yeah. What about this blue? How many wires in the blue bus?
3.
3? Why?
Is it self for n?
Well, this is a data bus, though. How many bits does MIPS crunch of data per instruction?
32.
32. We need 32 wires, because every wire's signal level, you know, from physics, there's only 1 voltage at a time on a wire. If you want to read a word of data, you need 32 wires. So for sure, this is, because it's MIPS, it's 32 on the data bus. Is there anything else we need? How many, this is great. Okay, so how many, this is great. How many words are in this data field of a cache line? This is 1 cache line. How many words of data? That's a problem. 2 words, okay. So that'd be like how many bits? Yeah, 64. How many bits of tag? Good question. It's the hardest of any of these. But before we see the answer, how many bits are in there in the tag? Well, we started with A was 8 bits total on the address bus. Remember, the tag is what's left over in our fields, right? So you start with 8 bits. This is the number of bytes per word, is a W. Okay. Then what's after W is M. You say, not in the alphabet I learned. Well, that's from the author, okay, but we go with it. So this is the number of bytes per word. This is the number of bits, number of words per block, and bits is a log, right? Of the number of bits, the number of words per block. And then what? This is the number of lines in the cache. And this is what's left over is with a tag. So tag is A minus the sum of n plus m plus w, or you can subtract all of them. If you multiply by -1, is what? 8 minus 3 minus 2 minus 2. Only 1 bit. Let's see. 2 bits of tag. So what did I do wrong here? And 3 bits.
That's what, 8 minus 7.
8 minus 7 should be 1. No.
Oh, 8 minus 4.
Where did I do wrong here? 2 to the first.
Yeah.
This is bad. See, Monday. No, 2. This is fine. This is okay. We had
Words per block is
words per. Oh, okay. Where's the W calculation? See. W calculation. We didn't ever do it, that's why. See, you had to be systematic. So the number of, this is solving the number of words per block is 2 to the m, right? 2 to the m equals 2 implies, no, 4. 2 to the m equals, no, 2 to the m is 2. So m must be 1. Okay, so 1 for this. So m was 1. I don't know where I came to. Okay. So that's 4, 5, no, we're still off here. 8, 3, 1, 2, we're good, right? So that's 4, 6 is 2, okay. 2 bits for tag. So if you look inside, you'll see 8 wires in the address bus. We're good with that. We know why, because main memory has 256 bytes. Memory is byte addressable, so I need 8 bits of address to specify which word, in this case byte, which byte of memory I'm going to access. And then what about fetching the data? Data has to go over the data bus. It's MIPS, 32-bit words. It registers 32 bits. What do we connect up here? We connect up straight through from the cache. What comes in, what comes out is the same in case we miss. They're the same widths. But what's different when we go to main memory, the data bus is what's actually the data value, and the address is what's on the outside is the address. It's a pointer to where the data is. This is the data bus. It's transferring the bits of memory. This is accessing memory as a pointer. We can actually see these on the circuit board. We pass it around. We show you a lot of pictures to keep reminding you. If I look inside the cache, there's 2 words sitting here. They're 32 bits each, so 64 bits, or 8 bytes. The tag bits is what's left over of what? Of the address. So we can think of the address going in here, and only the upper 2 bits, upper 2, that's the key, upper 2 bits being saved. We see that here, calculated here, and right into this format. This is the general formula. Okay, I'm taking it up a notch because we've seen this a couple times, and so I can explain it again, or we can try to use it. So we'll use it. What about the address map? If someone asks you to draw the address map, it's okay to use ellipsis, right? It's a fancy Latin word or some Greek, I don't even know, ellipsis. So you start 0, and then the next word is going to be byte address 4, and then the last, FF is actually this last cell, but the last word is going to start at FC, 0FC. Everybody's okay with it? Is this hex? In hex? Okay. So this is the range inclusive, is 0 through this inclusive, 256 bytes. I'll let you ask some questions on this. This is a good problem to know how to do, I think. Okay. So here we see the wires on this projector, not as resolution maybe, but we can actually see some of these wires here. It could be a multi-layer circuit board too. Sometimes the wires are, call them wire traces, can be between layers, but that's fine. We can see this happening here. So here's physically, it's important to know the physical view too, right? I'll convey to you guys everything that I can pass on. I just had somebody in office hours, it was same thing, it's like, right, you can learn the formula, but then you go to the next class, or time to get the next class, there's too many things. If you understand what it is, it's actually worth your time to do that. Another thing I like to convey to you guys is what's the physical part, right? If I just draw something on the board, it's important to know what it is. So what we've been talking about, where are all these things? These are the CPUs taken out of the socket here. But this is the CPU, contains the cache inside the chip today. Someone's going to vlog about years ago, the cache used to be external chip, which would make it slower because we have to go off the chip, further distance, a little more drive and so forth, more energy. And now because of Moore's law, you can put the cache right on the chip. Not only the one level cache, we can put all levels of cache on the chip and multiple cores on the same chip. It's pretty amazing. That's just in a few years, actually. So, any questions on the physical view, how this relates to the functional view? Okay. You know, I tried just memorizing stuff, and it got to be like, you know, graduate school, and then it'd be like too late in the night and studying, and all of a sudden you realize, oh my gosh, it's so easy if I would just take the time to understand what it means. And then so I just try to tell you that. So it's save you those Monster Energy drinks or whatever. Yeah. There's a bug. There is a bug. So now let's try another example. MIPS space system, 256 bytes of main memory. Well, we saw it before. 64 byte direct map cache. Kind of sound familiar. Well, I said two words. Internal memory layout of the cache. I think we already saw this. Right? Previous slide has that. Okay, so here's the writing the address bits as fields, okay? So if you're an electrical engineer, this probably is interesting to you. If you're a computer scientist, maybe this is more interesting to you, but it's the same problem. You're going to write the bits in terms of fields, okay? If you're a computer engineer, you have to know both, but that's okay because you're more useful, you see? People will can hire you to both jobs. Can come in handy. So here's the physical view inside the cache when we see these different fields. I think in this section I already jumped ahead and showed this, right? So we can go a little bit quickly, but now you can see each one of these fields is relating to the number of bits inside the cache in terms of address. So this is the address fields. 2 for the byte is a lower 2, which means we go up by 2 bits at a time, which means a multiple of 4, because 2 to the 2 is 4. So a multiple of 4, which we know PC plus 4 is the next instruction. Or, remember address, we had in the quiz, we had an exam, you have a sub I, it has to be multiplied by 4. A sub 8 was 32 offset. Now we see why, because of the address. And we access these in cache, this cache has 8 lines. Okay. 2 bits of tag, the word index, only 1 bit, see, left or right. If the bit is a 1, well, bit of 1 is a right over here. This bit is a 0, it means it's in the left slot or cell. What about if you have a 0, 1, 1 in that field? It's going to be then, where do I find it over here on the right? So this is like a puzzle, right? So if there's a 0, 1, 1 in the line field, I'm going ahead, 0, 1, 1 in the line field. I'm running out of space. So you have to deallocate cache. Running out of space. The 0, 1, 1 is in the line field. So there's multiple bits here, a total of 8 of them, right? 8 bits. But I'm telling you that the line field has this value. Is in the line field. It's 3 bits, line. So where do I see it? Where do I look for this? This is an address. So where do I look for that data to be stored in this physical device, in this memory? It's cache memory.
Line number 3.
Line number 3, starting from 0 is Neil's exactly right. So it's 0, 1, 2. So this is actually, these bits directly tell you which line of cache. Is that what it means? See? Line of 3 bits means those 3 bits tell you which line number it is. You say, that's it? Yeah, that's it. You can make it complicated, but take those bits of the address, and that's going to tell you exactly where it goes in cache under direct map strategy. You're going to say, okay, well, I finally understand direct map. Well, then we got to show you the next one, right? Make it more complicated. So, yeah, good. We're going to try a problem to put an arbitrary number and see where it goes in cache. But go ahead.
Line 3 would be
Yeah.
has 2 words.
Line 3 contains 2 words. That's correct. Because every in this,
Where are you
yeah,
getting those words from? From the memory?
that's true. Yeah. So this is your garage, and this is your closet. Okay. So all your clothes are. Well, I don't know. This is a public storage, right? We don't have basements here in Florida. Okay, but up in north, because we change seasons, right? You know, you go down to the basement and you get your winter clothes and you move them in the closet. Then it's summer and you put the stuff back, right? So this is small storage. This is the big storage. This is inexpensive but slow. Okay. Here is prime real estate. But you got to make some decision what you're going to keep there. What we're going to do is use temporal locality and spatial locality. Temporal locality says what? Well, if it just accesses it, it's going to be there. Because that's what we do, we overwrite it. How do we have spatial locality?
Grab more than one.
Jack's exactly right. You're going to grab 2 words at a time in this cell. You can see it over here. Over here. Wrong way. We got a new battery today, see? So you can grab 2 words at a time. So if you miss on a sub I, you're going to get a sub I plus 1, and then by the time the processor gets around to accessing ai plus 1, because I go in a loop, and it's already going to be loaded. That's nice, because then you don't have to wait for slow memory again. It's like putting things in a little container, right? We already know these. This is the cool thing, is that everything we show you here is, you put all your fishing, whatever you're into, right? What are you into? I don't know, fishing, tennis. You put it in like a little container, right? You go to Walmart, right? They sell these things. It's plastic containers, right? I put everything in there. So I just don't even think about it. It's time for fishing. I'm so happy because it's not too hot. You just grab the container. It's like a little pallet. It has everything you want right there.
What's the component of the valid bit? Because
Valid bit, yeah, valid bit's coming up. The main idea of valid bit is a quick way to invalidate all these. We don't have to. It's a way for us to keeping track. Is it winter or summer? Just to say, you know what, the stuff in that container it's not valid right now. It's just a little tag on the outside. That's more important when we update things. We haven't talked about writing yet. This is coming soon. So let's try an example to figure out. This is figure out the capacity of cache. Suppose you want to try. Remember, this one was maybe a little bit easy. Suppose I'm giving you an address, a random address, 1200. I want to find out in memory where address 1200 is going to be stored inside the cache. Now in memory, we know address 1200. We can imagine it in the memory map. So what's given is a direct map cache having 64 lines, and the block size is 16 bytes. Just 4 words is given on this machine because it must be 4 bytes per word, 32-bit machine. Which line in the cache would hold main memory address 1200? Sounds like a hard question. How do you solve the question?
we solve everything about once in a bit.
Yes. Come up with the field encoding. Once you have the field encoding in terms of bits, then I'm going to take address 1200, write it in binary, and then which of those fields will tell me where it is in the cache. I want to know which cache line. So everybody we just did an example, you can try more practice, right? Is coming up with these fields. Yeah. See, there's 4, right? So there's going to be 2, right? There's the block size is 16 bytes, which would be 4 words. So we need 2 bits for that, because 2 to the 2 is 4. And then 64 lines. We're telling you the units of lines. We're so happy because we don't have to do these calculations over here. So 64 lines. 2 to the n is 64, means n was 6. Tag is what's, do you even have to solve for tag for this problem? No, because the answer is in which field? The line. What is that? Well, here's 1200 in binary, and you're going to say, oh my gosh, I can't do that. Well, I agree, it's a little bit challenged, but we know it's, what's the closest power to? Yeah, 1024. So 1024, how much more is it than 1024? Well, it's going to be not 256 more, okay, not 512 more, not 256 more, but 128 more, and and then get this. Well, here it is. This is the field for 6 bits here. What number is that? You guys can handle that. 0, 0, 0, which just ignore that, right? So then you end up with what? 1, 0, 1, 1. What number is that in binary to convert to decimal?
11.
11. See the 11? 10 is 1010. 10 is tens, and 11 is like that. Ta-da.
The byte field always 2.
On MIPS. If it's 64-bit machine, you got to double it to 4. Yeah. If it's a little embedded microcontroller, it might just be 1. No. Here's alternate solution. This is what the author recommends, is you memorize these formulas, but we can do that too. So if you want to use the author's method, that's fine. We learn more. Remember, these are mod functions because we're wrapping around the cache. Every time we get to the end of the cache, we go back up. So another way we can solve this problem is figure out where it's in the cache using mods. So we start with 1200. We're going to figure out the block address because there's 16 blocks in the cache. How do we know that? Because this is actually the number of bytes, 16. So we're going to figure out that the block address is block number 75. What that meant is we start here at 0, we go to 15, and then 16 to 31, and how many times are you going to wrap around before you get to 1200? 75 times. All right. So then what? We figured out it's the 75th, okay, but then we have to put that in the mod of what we have. So that's 64 is the number of lines in this cache. It's given. So we take the address, mod the number of bytes in the block, we get the block number, take the block number, mod the number of blocks in the cache, which is the same as the number of lines, because block and line is the same. You're going to say, well, why do they use these 2 different words? Because block refers to memory and line refers to cache. It tells us where it is. That's going to be cache line number 11. It's the same thing we got over here. This is showing that mod, okay, of a power of 2 is the same as the bit position. Who's been telling you that since day 1? It's an easy way to do it. It's just convert it to binary, and the bits tell you the bits are doing mod for us, right? When we chop off some bits here, what did we do the mod? Well, we're actually these bits kept flipping as a power of 2 to the 4 is 16. Every time we increment a 1 here, it means we went around 16 times there on the block number. We just had to figure out which block number to start with is the first step. Okay. You can use either solution that makes more sense to you. It's fine. So now we're going to try to improve the hit rate. Let's understand the different types of misses that occur. When misses occur in cache, we have basically in this class, which is most of them, 3 different categories. One, I've been mentioning these words, compulsory miss. Compulsory means it's mandatory. It's required. There's no way. So cache is empty when we first start the program. We're always going to miss the first access. There's a way to improve this by something called prefetching. Prefetching gets back to heuristics that says, I think I'm going to need this block, even though I don't know yet because I haven't got to that part of the program. But I'm going to take some guess in that. That's prefetch. There's capacity miss. Capacity miss is when the cache gets full. Okay. The solution, easiest solution, is to increase the cache size. However, we had a certain property. We said small memories are fast and large memories are slow. Or the way the author said it was large memories are slow and fast memories are small. So when they make a memory larger, it's the same thing. If your closet's bigger and you're in a rush, you're wishing you didn't have such a large closet sometimes, right? Because you want to just find something quickly. If you don't have many choices, it's the easier thing to do. Now we showed we can use gates to do this for this comparison of bits to match the tag. What gate did we Boolean gate to see if two bits are equal? XNOR. And so we can do that pretty quick. Not a big job in binary, because checking if something's equal is actually pretty easy compared to picking out what clothes you want to wear. So we can increase the cache size, but there is some trade-off. Next thing is conflict miss. Conflict miss, we saw it in the case of a few of our address traces where the same line got used later in the program. We had to overwrite it, and then you want to reference it again, and guess what? You lost it. We saw Bilaty's anomaly as the extreme case of that. And we talked about this. So there's a couple solutions. You can increase the cache size or increase associativity, which is our next slide. I'm talking about associativity. So if I want to convert this to analogy in real life, okay, compulsory miss, prefetching would be, hey, the weather's getting nice now, so it's time to go fishing. I'm not ready to go fishing because it's a work day, but you know what? I'm in the garage, and I'm just going to prefetch that container. For the time I do access my fishing gear, it's already downstairs. About capacity miss, increasing the cache size, get a bigger closet. All right. Conflict, but it may be slower access. Conflict miss, we can bigger closet, or we can come up with a flexible mapping, which we're going to show you. It's fully, block can be stored in any line. The advantage is fully flexible. What's the disadvantage? The tag is going to get much larger. We have to check a lot of code check. When we're doing code check with direct, if we lose a lower digit, the attendant doesn't have to check the lower digit. So you can say, well, it's not that big of a deal. Yeah, well, for a human being, you can look at a number and see if it matches. Not that hard. But here we have to add additional gates to check all those bits. So set associative, we have k lines of storage block. The advantage is increased flexibility is kind of balanced against the tag size. We try some examples. So here's the diagram. It's actually from another book, but I like this one. It depicts functionally what's going on. So fully associative, this mapping from main memory to cache is flexible. Everybody see the pyramid? Where's the pyramid? See, this is the point of the pyramid, right? Well, registers are up here, right? So registers over here. So cache capacity less than main memory. So we're mapping main memory into cache. We transfer a pallet at a time. So that's the block. So the block has multiple words. I'm going to number them here. How many words in the block? Remember M? We just solved for M. There's 2 to the M words in the block. You can see them sitting here. They're numbered from 0 to 2m minus 1. Where do they go? They go in order on the pallet right over here. Which line? Well, it's based on the address. But remember our mod function? This is dividing memory into this many blocks. Our mod function is going to wrap around the cache. You put here, then you go here, then you come up, fill it up again.
Is the tag the same for that block?
Now, the interesting thing is in fully associative, we're going to have the tag be the entire part of the address besides the word within the block. Okay. Let me show you the answer, and then we'll come back. So this is actually the fully associative encoding. You can see here that we have a number of bytes per word, which is for MIPS would be 4 bytes per word. So this is 2 bits. As was mentioned, it was asked. Somebody asked, "Is always 2 for MIPS?" Yeah, always 2 there. But what about M? M is going to be variable depending on the design of the cache. Maybe you have 128 words per line or per block, maybe a 256. So it could be 7 or 8 bits here. The tag is whatever's left over. How many bits for A for MIPS? How many bits for MIPS for A. Address bus and MIPS processor is 32 bits, because, 32-bit word register. The PC, right, is 32 bits, we saw. So, how many bits in a tag? A lot, right? Each one of those have to be compared. That means a lot of gates. So the cache is taking up more area, more energy. Remember, we're accessing this all the time, comparing this thing all the time. So there's some trade-off, there's some cost. So let's try some problems and see how the numbers go. So now you've got a MIPS processor for a tablet. It's because MIPS is a 32-bit data path. You have 4 gigabytes main memory. It means all memory is fully populated. Right? 2 to 32 is 4 gig. Memory is byte addressable, so the units have to be bytes. 32-bit address bus. So we know these are 3232. Cache capacity is given is 4 words. It means 4 data words. The block size is 1 word per block, and now it's fully associative. So that specification looks like this. We see 1 word per block, not going in a row here, just 1. And the capacity is 4, so it must be 4 lines then to fill up that capacity. How big is a tag? Well, if there's only 1 word here, everything else is left over. It could either be 30 or 32, depends how you count it. If we want byte addressability, you would have 32. If you want word addressability, you only need 30 bits on the tag. But nonetheless, all the bits, because we only have 1 word here, are used for tag. This tag field is very large. Let's try another example. This example will actually show the transfer and the associative behavior with an actual address and doing the comparison of address. This could be a conflict miss on direct map. So here we are. So we always have to look when we give the problem: is it direct map, fully associative, or set associative? It's telling us the rules, right? How we replace data in the cache. This is fully associative. So that means that I can use up any of the space I have. I don't have to put it in a specific line based on the address. So the previous example, which we just designed it, the hardware, you have L load word, T1 from this address, T2 from that address, okay, is the offset with a base of 0 register, which means it's just this address. And here's another address. Sought, the cache transfers and the final contents. Okay. So what we imagine is transfers over the address bus. First, this address is transferred. Why? Because that's base plus offset. We know how load word works, right? Load word is base plus offset. Gets added together. That's this value. We're looking cache. Now suppose initially this is inside the cache. Is there a hit or a miss? Or we compare this address with what's in cache. Okay, there's a hit. So reference 1, what gets sent back to the cache gets sent back from the cache to the processor is the data. Data is 34. I'm just writing it as a decimal, okay? But there's the 34. How many bits wide is this? Well, it's 1 word, so it'd be 32 bits actually flows back, but I'm writing a decimal number. It could be any number. It could be a huge value, right? But that's the value that's at this address. It was cached. How did it get in here? It originally was out in memory. This is, address 048C, right? Up to this, see, ellipsis, right? Way down the page. It had the value 34. The first time it was referenced on a compulsory miss, that got pulled in and the address was saved. Later I'm going to compare. Well, now it's later. I reference this address, it's a hit. This comes back. So when I reference this address, does main memory have to get involved? No, because it's a hit. What about reference number 2? This is the address. I had a hard time. Is it C, I guess? It's a little funky. So C plus 0 is C. So this is the address we're looking for. We're going to compare it. Is C inside is that tag there? Answer is no. Okay. Since it's 1 word per line in this particular example, there's no spatial locality. So it could be like if there was, let's say, B here, C could be tagging along for the ride, or along for the ride. I shouldn't say tag, but coming along for the ride, but it's not. It's hard to make humor with computers. You can try it. It's hard, actually. It is really hard. So what happens? It's going to be a miss. We got to go to main memory. What data comes back? 7. 7 has to be written in the cache. Well, the way we're looking right now, is what kind of miss? Capacity miss. We have to overwrite something. A good question. What do you overwrite? There's different strategies, which is the next slides. You can pick the thing you used least recently, like most in the past, or you can pick the thing that you don't use too much, even if you just used it. Same as your closet, right? You know, we have this problem, right? You know, what I gotta put this, make space, or your desk, right? You know, I can make space for something. So we're going to talk about that's called replacement policies. But any questions on this access and how this would work with the fully associative cache? So we see a hit on the first reference, we see a miss on the second reference, but we got to compare the entire tag. When they're giving you fully associative, you don't have to worry about these too much in the details of the fields, because if we give you a simple problem with just one word, everything's in the tag. So here's some generic observation. The hits are serviced by the cache with a word transfer, so we see the unit of transfer between cache and CPU is a word. Misses are serviced by a block. Now in the last example, the block size is 1 word, so actually it looked like just transferring 1 word. But remember, you might have more tagging along. Main memory doesn't store any bits of address. It's just an index outside the post office box. So the address is the address on, you know, if your box 707 at the Alafaya post office, 707 is not taking up any storage space. It's just somebody wrote it on the outside with the tag. What's the tag? What's the tag? But what's inside is the data. That's your letters, that's your bills. And higher associativity, more tag bits, right? Higher associativity, fewer conflict misses. And fully associative, largest tag, but we avoid the conflict misses, only left with capacity miss. This is the address field. Again, the way to think about this, I calculate from the right side, starting with the bytes per word. That's usually from the architecture, from the ISA, instruction set architecture, will tell you it's a 32-bit machine, 64-bit machine. That's going to tell you how many bits here for this field. This is going to be based on the block size in words, not bytes, in words, block size in words. And here the tag is whatever's left over. How do you get A? That's based on the main memory capacity. So putting that all together, trying another example for fully associative. So this is kind of similar to what we had, except it's fully associative instead of direct. So the tags are going to be different. But you can see now here, tag is huge, 25 bits. As I mentioned, it's going to solve for this is 2, because we have 32 words per block. See, they were nice in this problem. They give you block size in words. Sometimes they're giving block size in bytes. You got to convert to words. Is it hard? No, but when you forget to do it, based on myself, yes. So you can double check your work, make sure the units is words. So the 32 words, it means 5 bits. 2 and 5, 7, started with 32, means 25 left. So let's look at the next and last design is set associative, which is a hybrid of the two, which is what most processors use for anything except L1. This is a two-way set associative, is the simplest of the set associative. Every block of memory has 2 chances, which means 2 ways. There's 2 ways that the data can be there. Way 0 or way 1. That's why it's 2 ways. It just means like there's 2 slots that are fully associative within each set. Okay, we want to see. So here we have main memory again, broken into blocks based on the block size. 2 to the A is main memory capacity divided by M. There's the number of block. So then what? Each one of these gets mapped to a set, but this is where the set is the mod, just like direct. Within each set, it's fully associated. It's like a little fully associative cache inside this set, if you want to think of it that way. So it's kind of a little bit like our coat check guy, right? He uses the least significant digit of the address to figure out which bin, but then inside the bin it's like random. So this is the bin number, is a set. Inside each set is fully associative, which means within a set we don't have any conflict misses. But the capacity is very small, only 2. But hopefully we don't have bad luck too often that we end up on the same set. It turns out, for most programs, this is the cool part, people studied this, okay? Just like you. Grad school students, a master's student, PhD student. If you give me just even 4-way or 8-way set associative, it looks like fully associative because the locality in a program says that the chances are that maps out of 64, that I need simultaneously in my what they call working set of the addresses that the program is referencing, more than 7 or 8 does not happen very much. So this is a way of giving the program the impression of fully associative with only making it having to search 8 instead of the whole thing. Now we don't actually search, we use hardware to do this, but still there's a cost. That cost is area, that's money, and also energy for all those bits to be checked with XNOR gates. So here's the field encoding. You're going to say, oh my gosh, there's another one of these things. And there's good news. Does this look like anything we saw before? Looks like direct. What's the difference? Replace line with set. And you say, that's it? Yeah, that's it. So remember line was N here, now it becomes S, and you just do the same thing all over again, okay? Sometimes they ask you how many lines there are, but they have to give you that and the problem. So let's try an example. So okay, this is the good news, one of our last ones is as hard as it gets, okay, but let's try it. So we're designing things, and we're going to see some Intel in a minute and some other chips and some MIPS and what these values are. So Zilog. Someone was in my office, we were talking about, he's actually in the other section, we were talking about 6502. They made a small 8-bit microcontroller. You can still buy it, actually. There's a funny story with this one. There was a guy I work with, and he had like a little embedded application for one of these chips. In the old days, we used to have chips in a dual inline package. You guys did in 3342, right? The pins are in a row, like 2 rows, right? It's like a rectangle. But he didn't use any of the upper address bits. And this thing had to fit in this little box, so what did he do? He cut it off with a hacksaw. It still worked fine. So funny story about Zilog. It used to come in I think it came in a 40-pin dip. But if you don't need, the cool thing about Zilog, it had all the address bits on one side, so you could cut it off. This is like, let me see, this is long-term memory. But let me see. I haven't thought about this for some years. I know, it's hard to make interesting things in computer engineering, electrical engineering. Let's see if we can get the pin out for a Zilog Z80, I think it was, right?
My Game Boy had one of those.
It probably did, actually, because they were used in some pocket games in the old. There it is. Oh, only $2 now. See, this used to be $200, but now no one wants to buy it. See, I think let's try to find the pin out. I think all the upper address bits are on the end. There's no cache in that thing, by the way. Well, this model, one of our problems is going to have some cache. But let's see if we see the pin out. Pin converter, that was pretty good. Let's see, it's better than me. I can type. Here we go. Let's see. Some people say pin out, or we could be digging into a lot of data here. Let's see if we can get a quick. Usually these are in the front of the data sheet or data manual. In this case, how big can it be? There. Let's see. No, not Explorer. I'm sorry. This is not a good trackpad, and my mouse is at home today. So what's going on here? Lenovo. I don't know what that is. Let's go back. Let's see. Close tabs. Is it here?
Usually it's somewhere in the beginning. You could use table of contents, but yeah.